Okay, in this video I'm going to go over the three different definitions for an acid and the three different definitions for a base. The first one I'm going to go over is Arrhenius. Arrhenius acids, this definition is just from your book. It increases the concentration of hydrogen ions. Make sure that you put this plus sign on there to show the difference between hydrogen and hydrogen ion. Hydrogen ions, they have to bond. They don't want to be alone. So what happens if we react something in water? So let's just say HCl, hydrochloric acid, reacts in water. This hydrogen atom on chlorine is more attracted to the unshared electrons on this oxygen. So the bond here breaks, and this hydrogen comes over here and attaches to the water, and it forms H3O plus and a chlorine ion. So this H3O plus is also called hydronium. Some worksheets will use H plus and H3O plus interchangeably, because that's essentially what happens. So we could write this without the water and kind of show the same thing. So we're increasing the hydrogen ions in solution, and we increase them because they attach themselves to water to form hydronium. So either one of these two reactions is acceptable. So this really covers what an Arrhenius acid does. This is the most specific definition that we have. We also have three different types of acid. We have monoprotic. This means that they just contain one hydrogen that can ionize. So ionize just means that it can break apart from its anion. So if we use this example, HNO3, and we react this acid with water, same thing that's going to happen. This hydrogen is going to come off because it's more attracted to this oxygen, and it's going to form the hydronium ion, and then the nitrate ion is just left over in solution. A diprotic acid, so di as in two, so here we have two hydrogens on our sulfate ion. So what happens, we can only lose our hydrogens one at a time. So the first reaction, just same thing we've done. Sulfuric acid reacts with water. It forms a hydronium ion. And since they can only react one at a time, we only lose one of these hydrogens. So we're left with HSO4, and it's no longer neutral. Hydrogens have a positive charge, so if we lose one positive charge, it's going to be a -1. So now this ion right here can react with water. So we get a second reaction going on in the same container. And again, this hydrogen is more attracted to oxygen than it is to sulfate. So it breaks apart, it forms hydronium and the sulfate ion. And now you probably get the idea here. A triprotic acid, we have 3 protons or 3 hydrogens that can break away. So we have 3 steps to our reaction. So now this hydrogen phosphate ion reacts. Dihydrogen phosphate. It forms the hydrogen phosphate, and so then we have a third step where hydrogen phosphate reacts to form hydronium and just the regular phosphate ion. This diprotic and triprotic a lot of times are referred to as polyprotic acids. So poly just means many. So we can break it down a little bit more into di and tri. Not everything that contains hydrogen is actually going to be an acid. So we have NH3, which is also called ammonia. it's actually a base. When NH3, well here, let me draw the Lewis structure for it and it'll make a little bit more sense. So our acid definition tells us we have to increase our number of hydrogen ions. What happens here, I'm going to draw a Lewis structure so you can kind of see what's really going on. The hydrogen in a water molecule is actually more attracted to these electrons in nitrogen than it is to the oxygen. So NH3 is actually pulling hydrogen away from water instead of adding to it. So then we end up with NH4 and a hydroxide ion. So since we're gaining a hydrogen instead of losing a hydrogen, this is considered a base. If we go by the Arrhenius definition, so Arrhenius base increases the concentration of hydroxide ions. So here we've taken a hydrogen from our water, we put it on our ammonium ion, our ammonia, and we formed an ammonium ion and hydroxide. So just because it has a hydrogen doesn't necessarily mean it's going to be an acid. And then letter B, not all hydrogens in an acid are released as hydrogen ions. So we talked about monoprotic and polyprotic. Well, here this is acetic acid. So if we look at the Lewis structure on it, CH3, C, double bond O, single bond O. In this reaction, we add this acid water, just this hydrogen is going to be more attracted to this oxygen, so it breaks off. And again, we form our hydrogen ion, and now all that's left is acetate. So not every single one of these hydrogens breaks away, only this very last one. And this is really why we draw, or we write out acetic acid like this, so we know that it's this hydrogen that's being removed and not one of these three. Alright, so the Arrhenius definition really isn't very good because it limits us to hydrogen ions in an acid, and it limits us specifically to hydroxide ions in a base. But we know that we can take pH paper or a pH meter and we can measure the pH of any substance and determine if it's an acid or a base. So Arrhenius, it's not really comprehensive. We need something a little bit better. So we get to Bronsted-Lowry. Bronsted-Lowry calls acids proton donors, and we usually do this in the form of a hydrogen ion. So remember, hydrogen, it had one electron, it gives that one electron away, and so now it's left with one proton. So if we donate a hydrogen ion, it's a proton donor, it's considered a Bronsted-Lowry acid. So if that's true about an acid, then the base is going to be just the opposite. It's a proton acceptor. So again, proton is going to be the form of H+. It's going to gain an H+. So if we just do a whole acid-base reaction here, we can classify one of these as an acid and one of these as a base. So chemically what's going to happen, remember nitrogen has those two extra pair of electrons. This hydrogen is going to be attracted to them. So we're going to form NH4 and Cl minus. So HCl gave away its hydrogen, it donated a proton. So this is considered my Bronsted-Lowry acid. NH3 accepted my proton, so it's my Bronsted-Lowry base. So if it donates a hydrogen, it's an acid. If it accepts a hydrogen, it's a base. So not everything is going to have uneven amounts of protons and electrons, but we can still determine if they're acids or bases. We can use a pH meter and determine that. So we needed a better definition than Bronsted-Lowry. So then we come up with the Lewis acid and base definition. This is the broadest definition. It puts everything in the category of acid, base, or neutral. It's a little excessive for high school chemistry, but you need to be familiar with just the term. So an example here, BF3, and then we're just going to say the fluorine ion. If you remember back when we did Lewis structures, boron is okay with only having 6 valence electrons. So if I were to draw this out, this is what we would get for BF3. So a Lewis acid accepts a pair of electrons, a Lewis base donates a pair of electrons. So then we have another fluorine ion. Well, this boron can hold 2 more electrons. It's got 2, 4, 6. We have our octet rule that says that we can have up to 8. So fluorine ion here is going to take 2 of its electrons and it's going to share them with this boron. So now we get BF4. So this boron accepted a pair of electrons. So that makes BF3 a Lewis acid. This fluorine ion donated 2 of its electrons, so that makes it a Lewis base. So everything can be classified as Lewis acids and Lewis bases. Not everything can be categorized as Arrhenius acid or Arrhenius base. There's one more term I want to cover, and it's called amphoteric. These are substances that have properties of both acids and bases. And the best example for this is water. If we react an acid with water, then water is going to act as our base. So this hydrogen is going to come over here. So this was a proton donor. So that's our acid. This is a proton acceptor. It's our base. Well, what if we react water with a base? So we'll take ammonia again. So this hydrogen is more attracted to nitrogen. And we're left with just hydroxide. So ammonia has accepted a hydrogen. It's accepted a proton, so it's a base. Water donated the proton, so it's an acid. So if we look between these two, water is acting as a base. It's also acting as an acid in a separate reaction. So this makes water amphoteric.